Hi, class 11, how are you? I been trying to record this video but was disturbed 2 to 3 times. I didn't know how to pause the video and all that, so this content I wrote previously. So I will repeat it for you and let me restart with everything. We have done some work in 6th chapter chemistry yesterday. I've seen a lot of work and I appreciate all of you. Everyone has done really good work. Alishba Akbar, her work was very nice and it was very making me very happy to see how she wrote the graphs and everything. I hope everyone will try more and with time it will get better. So today's topic is equilibrium law, which was previously called the law of mass action. 6th chapter is about reversible reactions, the reactions which can go in both directions. And chemists and manufacturers do not want it. They want more products. So in order to get more products from a reversible reaction, we have to use some tactics, some techniques, some approach to make sure that we get maximum products. And if we go into the pages of the history, the law of mass action is what we can take help from. The law of mass action was given by two Scandinavian chemists, Guldberg and Wag. Now, Scandinavia stands for Denmark, Norway, and Sweden, the Northern Europe. So anybody from Arab countries will be called Middle Eastern, right? Anybody from Pakistan, India, Sri Lanka, Bangladesh will be called, South Asian, So there are some regions in the world. Scandinavia is not a country, it's a region. And Guldberg, Wag belong to this region. Now, the law of mass action was given for the rate of reaction. As you all know, in a reversible reaction, when the equilibrium is achieved, there are two reactions taking place simultaneously with the equal rates. So rates are very much relevant with equilibrium. You control the rate, you control the equilibrium. So any law, like the law of mass action, which can help us understand the rates of reaction, will help us understand how to control the equilibrium and in the end the reversible reactions. So let's move forward with and understand what did these two great scientists observe from rate of reactions. Well, the statement of the law is the rate at which any substance reacts is directly proportional to its active mass. Now, let me make a few things simple. Active mass, let me call it quantity. Okay? Rate, speed. So the rate of reactions or the rate at which any substance reacts is directly proportional to its active mass. What does it mean? It means that if a substance is present in greater quantity, it is going to react faster. Does it make sense to you? Right? If a substance is present in greater quantity, that means it has more particles, more atoms, more molecules. More particles, more collisions, greater number of the reactant species will convert into the product and the rate will be faster. So it makes total sense. The rate at which any substance reacts is of course directly proportional to the active mass of that substance. And it's not a rocket science, it's a very simple law. But when we go to chemical reactions, there's not one substance, there are two substances. Generally, a reaction contains two reactants. So when we talk about the rate of one substance, we can say that the rate at which one substance reacts is directly proportional to its active mass. But what about for a reaction? All right, a reaction contains minimum two reactants. All right, so there are two active masses. Okay, and if you want to talk about the rate of a chemical reaction, it will be depending on both the active masses, like the product of the active masses of both the reactions. So the law will be completed as the rate, you can say with me, the rate at which any substance reacts is directly proportional to its active mass, and the rate of a chemical reaction is directly proportional to the product of active masses of reactants. I hope you can understand this fact. All right. For one substance, the rate depends on its active mass, but for a reaction, the rate depends on the product of active masses of both the reactants, because in reactions there are two reactants. So this law indicates that the rate, if you want to increase the rate, you have to increase the active mass of the reactants. You will obviously increase the rate of forward reaction. So this observation came from Goldberg and Wag. That's why it is called that's why it's called equilibrium law, because it is used in understanding and controlling the rate of chemical reaction, and that's how the direction of a reversible reaction. So now it's about time for me to explain more the active mass. Active mass basically is the mass that takes part in a chemical reaction, and we call it concentration. Concentration of solution. We will study in future what is concentration. But for example, you want to make a solution of NaCl. Okay, now you will make it in a solvent like water. One student, he takes 58 grams of NaCl. Now 58 grams NaCl, I think you guys know it's 1 mole, right? Let's add in a liter. It will be 1 mole per liter. Liter is same as dm³. If another student takes like 116 grams of NaCl, so what is this now? 2 moles? Perfectly right. Mole per dm³, mole per liter, same thing. If a student takes, let's say, half it, half will be what? 27.5. So 27.5, if somebody takes 27.5 gram of NaCl, I'm not sure if it is the half or not, you should just understand. It will be 0.5 mole per dm³. So in chemistry, the active mass does not mean mass in grams. It's basically the moles which are dissolved in a solution. So if you have a solution in liter or dm³, that's how you represent active masses, right? So if you want to go simple examples, like in our textbook, then you can say 4 grams of hydrogen. So how many moles is this? Of course, 2 moles. So 2 mole per dm³ is the active mass of 4 grams of hydrogen. So because we use solutions in chemical reactions, and solutions have a solvent and a solute. Solute is in the grams, so we take the molar quantities because mole is a more common unit for concentration, and solution overall is in liter. So this is the practical approach for the law of mass action for active masses. When it comes to representing active masses mathematically or on paper, we use square brackets. Yes, square brackets. Suppose if you have active mass of hydrogen, how will you represent it? You will put it like this. And what is this? This is active mass of hydrogen. For example, now tell me, what is this? Right? This is the representation of active mass of NaCl. So this is how it is done. So if you take any chemical reaction, let me make one, for example, N2 plus 3H2, okay, 2NH3. How will you write the active mass of nitrogen? It will become N2 in square brackets. All right. How will you write the active mass of hydrogen? Okay, H2 and exponent 3. Yes. If you are an improver or a class 12 student, you can obviously guess. But if you are in first year, this 3 mole, this quantity is represented as exponent when we are representing the active masses. Now, can you guess how you represent its active mass? Yes, NH3 square bracket. So what will be the exponent? 2. That's right. So when you are representing the active masses, one thing, you don't give the plus sign between them. Never do that. No sign. It shows multiplication when there is no sign. Never show any sign. And these moles, which are theoretical moles, they will be shown as exponents. So let me try one more time with you, and this time you will tell me how to write the active mass of this. Okay, let's say we have CH3 COOH reacting with C2H5OH. If you remember from yesterday's lecture, this is acetic acid. This is ethyl alcohol. Now, here ethyl alcohol is basic. It can give OH. And acetic acid is acidic. It gives H. So when H combines with OH, it forms H2O. And what are you left with? You're left with this guy and just this. So if you want to combinedly write them, how will you write them? CH3 COO and then C2H5, yeah, and this H2O. Now this is an ester. This compound is an ester family. You will study in class 12. But what is it called? It is called ethyl, because this is ethyl, C2H5, ethyl. This is acetic acid, so it becomes acetate. And this is water. So how will you write the active mass form, right? You can tell me, okay? Simply, right? You will write CH3 COOH and put them into a square brackets, right? No plus sign, right? And then you will make C2H5OH, put them in square brackets. This is the active mass of ethyl alcohol. There's one here, so there's one here. We don't write it pretty much every time. CH3 COO C2H5, and this is active mass of ethyl acetate, and this is active mass of water. So active mass practically is mole per dm cube. Convert the given mass into moles and then liters of solution. But when will you show it? How will you show it? You will basically show it by putting the formula of the substance in a square bracket. If it has any moles beside it, it will become the exponent. If it doesn't have, there's no problem. Okay, so I hope you are getting this now completely. One more try. This is the first try. This is the second try. Let's try one more time, right? Let's say you have a 2SO2 plus, I'm taking those examples which are from your textbook so that you find them relevant, okay? How will you write the active mass of SO2? You write SO2 in a bracket, and this 2, which is this 2 here, becomes the exponent. If there was 3 here, you put 3 here. Then O2 in square brackets. Power, no, power is 1 because there's 1, we don't write it. Here, SO3 and the power is going to be 2. So that's how you represent. This is how you represent. Representing from here. What is this? Representing active masses. Representing active masses. And what is this? This is how you take active masses in a laboratory. You have given masses which you can weigh on a physical balance. Then you can make moles of them, from the first chapter this is, and then a liter of solution will make the active mass of the reactant. So this is the general introduction to the equilibrium law. It is statement, active masses, how you represent them. Now the law of mass, law of mass action, here it's just introduction, but practically where we use it. To understand and actually get the maximum out of this law, we take another step ahead and we derive expression of equilibrium constant with the help of the law of mass action. Yes, equilibrium constant is obviously a number, a mathematical digit, a quantity, and that can further help us to control the direction and the extent of the reaction, reversible reaction. Yes, so you have to derive the expression of equilibrium constant Kc with the help of the equilibrium law. So I give the heading to derive expression for equilibrium constant. For now, I will tell you how we write equilibrium constant. We show it with Kc. Capital K, C for concentration. The symbol of equilibrium constant is Kc. This is a new term, mathematical term, and you will know with time what it is and how it is used. For now, we will study how to derive the expression for equilibrium constant Kc for a hypothetical reaction. Now, this is very important. Today's lecture is going to be a little bit long, I guess. So let us start with a homogeneous reaction. Let us take a hypothetical reaction. Let's say we have m moles of A, right? And they are reacting with, let's say, n moles of B, right? And they reversibly react to make x mole of C and y mole of D. So m mole of A, the reactant reacting with n mole of B. Now here there could be other reactants like 2SO2 plus O2, right? O2, n will be 1 again, right? So basically what happens in the examination, they ask us to state the equilibrium law, and then they ask us to derive the Kc's expression for different reactions, not just this. Sometimes this, but sometimes they give different reactions. So today I will be explaining to you those as well, or maybe they'll go by tomorrow for that one. So let's go and derive for this hypothetical homogeneous reaction. So according to the law of mass action, according to the what? The equilibrium law, right? Rate of forward reaction. Now guys, tell me, forward reaction depends on, as you know, the rate of a chemical reaction depends, directly proportional to the product of active masses of the reactants. So forward reaction depends upon the active masses of these two, their product. So this is how you show directly proportional. Do you mind? Right? And how you write the active mass of this? Can you tell me? Square brackets, A, and where does the M go? M goes here. And then no sign, no plus, nothing. The product just B And where will the N go? N goes here. Easy. So the rate of forward reaction is directly proportional to the product of active masses of the reactants. And now you already know how we write active masses, right? Now, if you guys know about the proportionality and the sign of proportionality, right? It converts to an equals to, but there is a constant of proportionality. Let us say it's K1 in this case. This gonna be the same, nothing changes. This is, my friend, our first equation. Proportionality is a relationship. It does not equal the sides. Equality, it means this and this are mathematically equal, right? Similarly, if you want to talk about reverse reaction, guys, reverse reaction is also taking place in reversible reactions. So, can you tell me now rate of backward or reverse reaction? Now, if you're listening to me, guys, okay, should I give A, B? Oh, what do you guess? You have guessed right. C, X, and D, Y. Nothing in between them. This is the product of active masses of products. Now, products, different. Product, multiplication. Products. Okay? So, now again, the rate of reverse reaction is equal to, if here we have K1, we can take here K2. K2, C power X and D power Y. This is the second equation. So first equation represents mathematically the rate of forward reaction. The second equation represents mathematically the rate of reverse reaction. But what happens at equilibrium? At equilibrium state. What happens when there is equilibrium? Can you tell me? Yes, the rate of forward reaction is equal to the rate of reverse reactions. Now, if you see the above two equations, this one and this one, these two equations, the rate of forward reaction is the left hand side of the first equation. Rate of reverse reaction is the left hand of the second equation. So if the left hand sides are equal, right hand sides are equal as well, if you know from simple maths from class metric, right? So I will write K1 A power M B power N equals to K2 C power X and D power Y. Now, if you know cross multiplication, guys, you can put K2 under K1. So K1 upon K2. And these two will go down. So you have C power X, D power Y, A power M, and B power N. Now, the product of active masses of reactant becomes the denominator, and the product of active masses of products is the numerator in this fraction. Now, K1 and K2 are both constant. We can write one constant for both of them. That is Kc, the equilibrium constant. So C power X, D power Y divided by A power M, B power N. Now this expression, this third expression is called equilibrium constant expression, and the Kc is called the equilibrium constant. We can write here, this is called equilibrium constant expression, because it is telling us a relation between equilibrium constant and the active masses of the reactants and the products. So how it is showing us, we will discuss that. Here Kc is called equilibrium constant. Now the number 3 equation, the entire relationship, is called equilibrium constant expression, and the Kc is called equilibrium constant. Now guys, if you take, this is a hypothetical reaction, but if you take a real reaction and if you could somehow calculate the concentration at equilibrium, both the reactants and the products, and you divide them, the ratio will be a real number, which is called Kc. And you can, if you have 10,000 reversible reactions, you can write 10,000 radius of Kcs and make a chart of them and maybe use them in order to predict direction or control direction and extent of reactions. So Kc is a really very valuable mathematical constant for the reversible reaction. By definition, it is the ratio, of course, of what? Product of active masses of products, okay, to the product of active masses of reactants. Now if you are asked to define it, you will define it how? The ratio of the product of active masses of the products to the product of active masses of the reactants is known as the equilibrium constant. You can write it in words. The product of the ratio of the product of active masses of products to the product of the active masses of the reactants is known as equilibrium constant. The different chemical reactions have different chemical equilibrium constant. This is how you derive it. Okay. Now, deriving the equilibrium constant expression and writing it is different. Suppose I have a reaction N2 plus 3H2 double arrow, and it is 2NH3. Now, if you ask me to write the equilibrium, write, all right, WRITE, write equilibrium constant expression, I will write what? I'll write Kc is equal to, on the top, numerator, products. So we have only one. At the lowercase denominator, the reactants. So we have 2. N2 and H2 power 3. No sign in between. This is how you write equilibrium constant expression. It's very simple. You can write for any chemical reaction their equilibrium constant expressions. But if you had to derive it, then you will put this equation here. This line remains same. Here will be N2, right? N2 and then H2 power 2, and then equals to same here, just 2NH3. So everything else will follow, and you will reach this thing here. So if in the examination, if they ask us derive the equilibrium constant expression, that's different. If they say just write, write is very easy. Right, it's very much simple. You can write very easily the equilibrium constant expression for any reaction. So writing is different, deriving is different. Okay, so equilibrium constant Kc, here the C stands for concentration. Initially, liquids and gases, they all were dealt with Kc, but it was found later that if the reactants and products are all gases, most results from Kc mathematically and practically were not equal. So there was some problem with the Kc of gases because gases don't have mass, grams. They have moles. They have partial pressures. We don't measure gases in terms of their masses. If you go to a CNG station and you get a CNG, compressed natural gas, for your car, all right, and then he tells you you got 2 kilo or 4 kilo gas, he does not mean kilogram, he means kilopascals. All right, so gases are not taken in terms of masses but in terms of pressures, the quantity of gas, because gas volume, gas laws and everything, gas volume is pretty confusing thing here. It changes a lot. So we don't take the mole per dm cube is not an accurate measurement for gases. So atmosphere or torr or pascals is a better way. So in case of gaseous equilibria, when equilibrium, when you have all gases, let's say you have A gas with B gas as reactants, and you have C gas and D gas as products, then in that case they don't have Kc. Their equilibrium constant is then represented with Kp, and it's the ratio of Pc, partial pressure of C, Pd, partial pressure of D. So the numerator is still the products and denominator is still the reactants, but just in terms of active masses, there are partial pressures. So partial pressure, all of you guys know, the pressure exerted by a single gas is called partial pressure. So gases have Kp and solids, liquids have Kc. Kp is for gases. It is the ratio of the product of partial pressure of the products to the product of partial pressure of the reactants. However, Kc is the equilibrium constant in terms of concentration. It is the ratio of product of active masses of products to the product of active masses of the reactants. All right, I hope you get all this. It's a pretty long lecture today. I hope you understand it. But wait a minute before we end it. If in examination they ask us derive the equilibrium constant in terms of pressure, Kp, you can do the entire process again. But instead of writing the active masses, write the partial pressures like PAPB, PAPB, here PCPD, PCPD, here same, and the K1 upon K2 will become Kp. So Kp, my dear friend, however, we do not calculate Kp like this. Mostly Kp is found from Kc, and tomorrow I'll teach you that. But for today, if in examination we don't know what they can ask from us, we can do it that way and we can also derive it. So that is the topic for today, my dear students. I hope you enjoy the lecture. You will require to do lots of pausing and then rewinding, and that's the advantage of a video lecture. So I will be waiting for your work and be creative, add some nice things and try to make it more creative. All right, thank you so much. See you tomorrow again with some new topic. Goodbye.